Hi, welcome to this online lab demo. Today we shall be going through together the design of a T-matching network specifically targeted to optimally drive a 90 ohm load from a power source which has a source impedance of 50 ohms. In addition, the matching network should abide to the following specifications. Mainly a bandwidth larger than 1.67 GHz and a resonant frequency of around 1 GHz. In order to aid our design, we shall be making use of two open source software packages, mainly Cooks and Smith, which are readily downloadable from the net. You may also find this piece of software from your VLE space. Let us start the design by first considering the quality factor of the network. In fact, as already covered during the last lecture, the quality factor of any matching network defines its bandwidth. And as we can see here, the overall quality factor is given by the ratio of the resonant frequency of the network to the bandwidth. In this case, we notice that an overall quality factor of 0.6 is required. Noting that this value is quite small is in fact indicative of the broadband nature of the frequency response required. In order to permit us to use the Smith chart and of course simplify our design procedure, we can use the following approximation in which we know that the nodal quality factor is related to the overall quality factor of the network by this relationship, in which Qn is approximately twice the value of the overall quality factor. So in this case, the maximal nodal quality factor approximation will be used and will require a value of 1.2 in order to achieve the required bandwidth. So let us start our design by launching our Smith software, which is an interactive Smith chart tool. The first thing that we need to do is to define the 1.2 nodal quality factor contour. First we look if it is readily available on this side. In fact it is not, and so we need to insert it directly ourselves through the keyboard, and we see that it is plotted automatically on the ZY parameter Smith chart, in which the blue lines are the Y parameters and the Z lines are the Z parameters. Now, we need to first define our starting point and our end point. So we start by the load, we go on keyboard, we insert the load. In this case, since the load is resistive, we need only to insert the real part and the imaginary part is set as 0, and then we need to define the frequency, the resonant frequency, but since the software has a default value of 1, this will remain unaltered. We insert the source impedance. Once again, the imaginary part is 0 since it is a real or resistive termination, and the input frequency needs to be of 1 GHz once again. So the idea is to go from this point to this point by touching at some point this 1.2 nodal quality factor line. So since we are going to design a T matching network, we require to have two series components and one shunt component. Of course, there are a variety of ways, as we have seen in class, how to design this. So I'm going to take one possible path, and then of course you can repeat the other paths at your own time at home. So I'm going to start my design with first inserting a series capacitor, whose value will be of approximately 2.65. Then the shunt component will be a shunt capacitor of around 0.605 or 606 femtofarads, and finally a series inductor of around 9.7 nanohenries. As you can see, I have started first with the 2.6 picofarads in order to be able to intersect with the orange contour line of the nodal quality factor, so that in fact at point 4 we are seeing here a nodal quality factor of 1.2. In test point 5, in fact, we can also notice that the input impedance seen at this point is in fact approximately equal to 50 ohms. So, with this in hand, we can simulate the response of the network so that we see if our design is correct or not. So we launch COX, which is another way of saying it's a quite universal circuit simulator. In fact, it's a generic simulator specifically designed for RF circuit design. And using this drop-down menu, we start choosing the lumped components first. So we place a resistor, then we insert an inductor. Notice that here we are seeing the circuit from the other side, since this Smith starts with the load. We have a shunt capacitor, a series capacitor, and finally the load. The neater you draw the circuit, the better, so that if we have any particular issue, we can easily debug it during our testing. We need to define also an AC voltage source, and as you can see, it is very convenient that the default value it gives is of 1 volt, and so by defining the output voltage across the resistor we have here, we can determine directly the frequency response of the gain by measuring directly the output. Remember always that in the simulation of any circuit, you need always to have a reference point or a ground point so that the simulator is able to do the calculations. So once we draw the circuit, you can change the values according to the values obtained using the previous software Smith. So this should be of around 0.606 picofarads, and this should have a value of around, let me go back a bit, so it should have a value of 2.6 picofarads. And finally, this should be 80 ohms. We save, and COX gives us the facility to define equations so that we can compute more complex relationships in our simulation. So we can calculate the gain of this network in dBs, in decibels, by using this expression. Notice that whenever we have V out, that's the node name, and dot V means it is the frequency response values given to us by the AC response, which we will define in the next steps. Apart from the gain frequency response, it would be also convenient to have an idea of the return loss and the input resistance seen by the source. So all I'm going to do is copy again these components, and instead of using a voltage source, I'm going to use a power source. Once again, I insert a reference ground and define two new equations. the first equation that I'm going to define is the return loss, which is dB S11 a minus 1 to that, and we can also have a value for the input impedance, which, as we did during the last lecture, we can relate it to the S parameters. Note that in this case we will get only one S parameter, since we are doing a one-port measurement, since we have only one power source or one port. So the expression, as you recall from class, is as follows. So we are almost there. The final step that we need to do is just to define our simulation. So we go to the drop-down menu, we select simulations, first insert an AC simulation and an S parameter simulation. So the AC simulation will be used for this network, and the S parameter simulation will be used for this network. And we need to sweep logarithmically from 0.1 to 4 GHz for around 2000 points. You select as much as point as you would like to have your graph to be accurate. You do the same for the next simulation, and you save and you simulate. Now you get a new canvas on which you can place any type of result. In this case I'm going to go for a Cartesian graph, in which first I'm going to plot the input impedance. So as you can see, at 1 GHz I got approximately 1 GHz. This is not 1 GHz, we can be a bit more accurate. I'm going exactly at 1 GHz, it's approximately equal to 50 ohms. Okay. Then on the same graph, but maybe on a different y-axis, you can choose between left or right axis. So we go on return loss, and we are going to plot that on the right axis now. And as you can see, the return loss at 1 GHz is very high, which is optimal, since this means that we are matched at that frequency. And finally, we need to check our bandwidth if it is more than 1.67 as required. So once again, we drop a Cartesian graph, we choose gain, and as you can see, it is a bandpass response as expected from the circuit that we have. As you can notice as well, at 1 GHz, at approximately 1 GHz, we have the maximum power transfer point, which is around -4 dB, and we can determine the bandwidth by seeing where we have the -3 dB point, which occurs at this point at -7, since it is -3 dB less. So that point there and that point there. So we have these two values. So as you if we calculate 2.21 minus 0.4, we'll get a value of 1.8. So as you can see, our designed matching network